Have you ever felt like algorithms are just this scary, super abstract math thing? Yeah, let's forget all about that. Today, we're going to crack open a coder's secret recipe book. We're going to look at algorithms for what they really are, which are just these elegant, powerful, and honestly, surprisingly simple recipes for solving some of the biggest problems in tech.
I mean, just stop and think about it for a second. How on earth does your map app figure out the absolute fastest way through that crazy rush hour traffic? Or how does a streaming service just seem to know you and recommend the perfect next show to binge? Well, it's not magic, right? It's a set of these brilliant recipes we call algorithms, and we're about to check out the essentials.
Okay, so let's flip open our cookbook. First up, we're going to look at recipes for finding those needles in haystacks. Then, we'll become maze explorers. After that, we're going to get into mastering long sequences of data. And finally, we'll check out some master chef-level techniques for building smarter solutions to really huge problems.
All right, first things first, let's talk about finding stuff and exploring complex spaces. This whole first part of our toolkit is all about search and navigation. And it doesn't matter if that's through a sorted list of numbers or, a huge social network.
So our first recipe is an absolute classic, binary search. This is your go-to when you need to find something in a sorted list and you need to do it lightning fast. The analogy here is perfect. Imagine you're looking for the name Smith in an old-school phone book. You're not going to start at A, right? Of course not. You flip it open to the middle, you see you're at M, and boom, you throw away the entire first half. You just keep doing that, cutting the problem in half every single time. That is the beautiful efficiency of divide and conquer.
And here's that recipe in code. The real magic is all happening inside this while loop. Just think of L and R as your left and right fingers on the ends of the phone book. Every time through the loop, the code finds the middle page, checks it, and then moves either your left or your right finger inward. It's literally the code version of ripping out half the book again and again until you land on the exact page you need.
Next up, we've got this wonderfully clever technique called two-pointers. Its specialty is finding a pair of items in a sorted list that fits some condition, like, say, two numbers that add up to a target value. So imagine you've got two fingers on a bookshelf. One starts at the very beginning, the other at the very end. They just start moving towards each other, checking the books they're pointing at. It's just a super efficient way to scan from both ends at the same time.
And the code, well, it reflects this perfectly. Our two pointers, L and R, they start at opposite ends. Inside the loop, we check their sum. If the sum is too small, this line here, L plus equals 1, it just nudges the left finger forward to a bigger number. If the sum's too big, R minus equals 1 brings the right finger back to a smaller one. It's this simple, elegant little dance as they close in on the target from both sides.
Okay, now let's move on to exploring networks, or what you'll often hear called graphs. Breadth First Search, or BFS, is our first tool for this. It explores a network layer by layer, kind of like the ripples spreading out from a stone you toss in a pond. It's what social networks use to suggest friends of friends, and this makes it absolutely perfect for finding the shortest path in terms of steps or connections.
Now, the secret ingredient for this recipe is something called a queue, which you can see right here in the code. It works exactly like a waiting line. We add our starting point. Then this while loop gets to work. It pulls the first item from the front of the queue, checks all its neighbors, and adds them to the back of the line. This simple process guarantees we explore everything layer by layer, just like those ripples in the pond.
Our other network explorer is Depth First Search, or DFS, and it's pretty much the complete opposite of BFS. So if BFS is wide and kind of cautious, DFS is deep and adventurous. It's just like navigating a maze. You pick a path and you go as deep as you possibly can. And when you hit a dead end, you backtrack to your last choice point and you try the next path. It's all about going deep down one branch before you move on.
The code for DFS uses this really powerful technique called recursion, which is just a fancy way of saying the function calls itself. See this line right here where DFS is calling DFS again? That's the code literally taking another step deeper into the maze. When it runs out of path, the function just finishes, and it automatically backtracks to the previous step to try a different direction.
So what happens if your map has, distances or travel times on it? A simple BFS isn't going to cut it. And that's where the legendary Dijkstra's algorithm comes in. This is basically the core logic inside your GPS. It finds the absolute shortest path in a network where the connections have weights or costs. It does this by being smart and, well, a little greedy. It always explores the path that currently looks like the best bet, the closest unvisited point.
The magic ingredient for Dijkstra's is this heap queue module, which is a special tool also known as a priority queue. Now, unlike a regular line that's just first come, first served, a priority queue always serves the most important item first. And for our GPS, most important means the path with the shortest total travel time we've found so far. That's exactly what heapqueue.heappop is doing. It makes sure we're always checking the most promising route next.
All right, time to shift gears. For the second half of our recipe book, we're moving on to mastering sequences of data and looking at strategies for taking on these incredibly complex problems by just breaking them down into more manageable pieces. So let's kick this off with the sliding window. This is a brilliant technique for analyzing a continuous slice of a long list or array. Like, imagine you need to find the 7-day period with the highest sales in an entire year. Instead of recalculating the sum for every single 7-day period, which should be a ton of work, you use a window that just slides along, adding the new day's sales and subtracting the oldest day's sales. It's just incredibly efficient.
And the code really shows just how efficient this is. I mean, after you get that first sum, the real magic is in this one line. Current sum equals R of I minus R of I minus K. Instead of re-adding everything, we just add the new element and subtract the one that just fell off the back of our window. That's the slide right there in action, saving us a massive amount of computation.
Next up is a fantastic little pre-computation trick, the prefix sum. The whole idea here is to solve a problem before you're even asked. If you know you're going to need to find the sum of different parts of a list over and over, you can create a new list where each element is the running total up to that point. Then, finding the sum of any slice becomes just one simple subtraction. It's like having the answer ready before the question is even asked.
So, the code is basically a two-step process. This first loop here does all the hard work up front, creating our prefix array with all the running totals. But after that, the payoff is huge. To find the sum of any slice you want, it's just one simple subtraction, like you see in the comment there. We've essentially made all future calculations instantaneous. Here's another really clever pointer technique: fast and slow pointers. This is the perfect recipe for problems that involve cycles or maybe finding the middle of a list when you don't even know how long it is. The best analogy is a racetrack. You've got two runners starting at the same time. One runs at a normal speed, the other runs twice as fast. Now, if the track is a loop, what's going to happen? The fast runner is guaranteed to eventually lap and meet up with the slow runner. And the code perfectly captures this little race. The slow pointer moves one step at a time, while the fast pointer leaks 2 steps. The entire algorithm really just boils down to this one simple check: if slow equals fast. If those two runners ever meet on the track, we know for a fact that we are in a cycle. It's just a beautifully simple proof. Okay, now for a true powerhouse strategy: dynamic programming. This is how we tackle enormous problems. We do it by breaking them into smaller, overlapping subproblems. But here's the key. We solve each small piece just once, and then we store or memolize the answer. That way, the next time we need that answer, we just look it up, instead of redoing all the work. It's the ultimate principle of don't do the same work twice. So, the Fibonacci sequence is the classic example to show this in action. To calculate, say, fib of 5, you need to know fib of 4 and fib of 3. But to calculate fib of 4, you also need to know fib of 3. Without a memory, you'd end up calculating fib of 3 twice. That's where this code shines. The memo dictionary here, that's our brain. The very first thing the function does is check. Hey, have I solved this before? If the answer's in our memory, we return it instantly, saving just a ton of work. And our final recipe today is backtracking. This is our go-to for solving problems where you have to explore a huge number of possibilities to find a valid solution. Think solving a Sudoku puzzle. You can think of it as building a solution one piece at a time. You make a choice, you move forward, and if you hit a dead end or you break a rule, you backtrack. You undo your last choice, and you try a different one. It's a systematic but exhaustive search. So there you have it. We've just opened up a 10-recipe cookbook for coders, and we've seen how some simple logic can power incredibly complex technology. You know, these aren't just abstract concepts for a whiteboard. They are patterns for problem solving that are literally all around us. So the final question is this: now that you can spot the patterns, what everyday problem could you solve with a code recipe?